Hi, kids. All right, we're going to talk a little bit more about Faraday's law and the equations and hopefully make some sense out of it. Um, but you should have already done the PhET simulation, and you can see, hey, if I have this bar magnet and here's my loop, so this is my area that I'm worried about, okay, that, you know what, I will induce a voltage across this loop as long as the flux is changing. So let's say this loop is being pulled down. So right now I have 3 field lines going through it, and if the loop gets pulled down, now I only have 1 field line going through it. Well, that means my flux would be getting less, so I have a changing flux, so the rate that that flux is changing would cause a voltage. And again, yes, this is just voltage, so you could still use your very nice equation. If I told you the resistance, if I said, hey, you know what, we have a resistor in this circuit, so there's my resistor, and you could then figure out what is the current flowing in that circuit, you know, something like that, okay? But hopefully that makes sense. Here's the other piece where this fits in, and again, you are gonna, well, let me do this first. So, you know, if you had a graph of flux versus time, if it was something like this, well, that would be, you would get no voltage. Why? Because there's no change in flux. If you had something like this, well, that means my flux is going down, versus something like this, hey, my flux is going up, which means my voltage would be going one way versus the other way. You can kind of think of it as, you know, if when we talked about our ponds, it would be something like this versus something like this. So that if you had, maybe this one would be this setup, this one would be this setup, okay? So that if the magnitude of the slopes are the same, the voltages would be the same, but it would cause the current to flow opposite ways. That's really all that's saying. And then the other thing that you need to be aware of is this, that even if you just have, let's say I have a magnetic field, and I have a bar, okay, in this magnetic field, and this bar is moving this way. Sometimes on the AP test, I've seen it where they say, hey, you have an antenna, and there's an antenna moving in a magnetic field. This bar, even though it's not a whole loop, will still develop a voltage across it. And you might think, well, geez, how is that possible? Well, mathematically, here's how it's possible. So if I'm just going to do change in flux over change in time. Now, the negative piece I'm not going to worry about. We're going to talk more about that tomorrow. It's just going to tell you the direction of the voltage. But flux is BA and then cosine theta. So really I have BA over T. A is going to be typically, let's say, length times distance. Well, D over T is that, so I'm going to get BLV. And if you look on your equation sheet, you will see right there, hey, there's Faraday's law, and right there is this equation. So you don't even have to have a whole loop to have a voltage across it. But here's where this actually makes sense. Let's pretend that this bar, I'm going to make it a little bit fatter, that this bar is full of charges. Because you know what? It is full of charges. Okay? Well, what is going to move? Electrons are going to move. So I have electrons moving to the right. So therefore, if I do my right-hand rule, my thumb would have to point to the left. My fingers would point into the page. So my force would be to the bottom of the page. Well, that means as this thing moves along, you're going to get a collection of electrons at the bottom of the bar. Well, where did those electrons come from? They came from the top of the bar, which means the top of the bar is going to have a positive charge. Do you see, as this thing is moving along, I have just separated the charge, therefore I would induce a voltage. And that voltage would be determined by the length of the bar, okay, this would be L, how fast that bar is moving, that would be V, and the size of that magnetic field. Okay? But it all relates, it all goes together. Hopefully that makes sense. Bye, kids!